Okay, so let's start with some more, I would say, advanced technique, because we are going to use some coding this time. I will show you that there are some things that can be achieved by using standard Grasshopper methods, but in the end, we will need absolutely to shift to Grasshopper Python to write down some scripts. It won't be too hard, but I strongly recommend that you learn Python if you want to create some more advanced growth algorithms. Okay. So first of all, what we are going to do right now is program some type of dynamic growth, which is called, in these fancy names that normally are given to technologies or technological stuff, it is called differential growth. Well, first of all, let's start with some very basic algorithms. What I'm going to do right now is simulate a growing three-dimensional mesh using voxels, because it's the simplest way to do this. So basically, voxels are three-dimensional pixels, and they are basically mesh cubes with a given length for the side. So what we're going to do is create some kind of growing point cloud, and we will give volume to this point cloud by converting each point into a voxel. And the property of voxels is that when they get close to each other and they interfere, then they blend and create one single mesh from the fusion of various voxels. So what we're going to do is create some loops that we already know how to do this, and inside these loops this time we will be creating some growth for a given set of geometries. What I'm going to use right now, just to prepare for the next step that will be effective mesh three-dimensional growth, I'm going to use a triangular mesh, triangular mesh. It's not the correct way to name it. It's a mesh made up of triangles. Okay. So what I'm going to do, I'm going to create a mesh box, and I will tell you why I'm going to use this technique right now. So the mesh box is not a mesh with a given x, y, and z dimensions. It's the conversion of a B-rep box into a mesh with x, y, z number of polygons in the three directions. Okay, so the dimension of this box are given by the base box that we have here. So what I'm going to do, I'm going to create a mesh box with one polygon per side. Okay, so I'm going to plug this here, here, and here. And so we have this initial mesh box. It's like one giant voxel, if you think about it. But anyway, and in order to give some higher resolution to this object, I'm not going to use standard Grasshopper methods like, I don't know, converting a B-rep into a mesh with a specific quality or resolution, or using the mesh surface command, which I would recommend instead of the mesh B-rep command. No, I'm going to use a kangaroo component. Pay attention that it is not a standard Kangaroo 2 component. I am going to use a Kangaroo 1 or 099 component, which is called the mesh machine. In Kangaroo 2, you will find a simple remesh. Okay, so it's basically the same component, but you will see that these two components here, they work in a different way. I'm going to use mesh machine because it has an output which is basically already a plankton mesh, while the simple remesh is giving us a remeshed result. Okay, Now, in this first definition, I'm not going to take advantage of the plankton mesh definition. But as soon as we know how to work with this, we will also know how to apply it to a real mesh three-dimensional growth. Okay, so if we want to work with a mesh growth algorithm, I do recommend that you eventually use a mesh machine command at the beginning of the definition. So what we are going to do, we are going to take this mesh box here, plug it into the geometry, and what we want to do is remesh this box using a specific length for, or well, a target length for the edges. Okay, so this mesh here measures something like 20 by 20 by 20. So what I'm going to say, I want a length of, well, let's say 5.00. Okay, so we have a length variable between 0 and 10. Of course, I cannot reach 0 as the edge length. Just think about that. If we reduce this value, decrease this value at 0, we will have an infinite number of edges along the three sides of this cube. So I'm going to take some precautions here. So I'm going to say that the minimum value for this edge length basically is going to be, well, let's say 2. Okay, so 2 means we will have 10 polygons in the X, Y, and Z directions. So this will be high resolution, low resolution. I'm going to start with low resolution as always, because I do recommend that you don't stress the machine unless it is strictly necessary. So this is going to be our remeshing rule. There are a bunch of inputs here that I'm not going to talk about, but you can eventually play with them. I would only name the first two, which is fix C and fix B. They allow to maintain fixed geometrical properties of the original geometry that we are remeshing during the remeshing process. So for example, you can keep curves or vertices fixed during the remeshing process. Okay, this allows for a better control of the remeshed geometry. What we are going to do is simply activate the reset. You see that true is initialized and false is running the remeshing. It's important that here you use a toggle which is set to true. True doesn't mean remesh. True doesn't mean reinitialize the remeshing. Okay, we will see this in a while. What's the meaning? So each time you set this to true, the mesh machine initializes, and when you set this to false, it is calculating the remeshing. Okay. Now the result of this is a plankton mesh. As you can see, we will plug here a panel. So let me get rid of paths and indices, and this is our result. If you install the Plankton library, I do recommend that you do this. And by the way, I just placed here a link to download the Plankton library. In case you don't have it, you must go to this URL, and I will copy this URL in this video description in below the video. So if you do this, you will have into the params geometry set of components. You will also find the Plankton mesh component, and the mesh machine has no preview, as you can see. But if I plug this into Plankton mesh component, you see that something here is actually showing up. Okay, so this is the remeshed box with a target edge length of 10. Now, if you decrease this, you see that this remeshing is actually increasing the resolution of the mesh. Of course, if I increase the resolution, I will have a mesh that resembles the initial cube in a better way, of course. If I increase back this, it's very unlikely that I get the same result. You can see that I don't get the extremely low resolution mesh that I had at the beginning. So if I want this, I must initialize the mesh machine once again and then hit false once again. Okay, so it's just like resetting the mesh machine component. And if you want a real-time remeshing occurring on this mesh cube, you can plug a timer to this component. So each second, this component is actually recalculating the mesh. And I would recommend that if you want a seamless correspondence between the plankton mesh and the resolution that you are defining here, you set this to a very low time interval. So in this case, you see that the mesh is updating basically in real time. Okay. So this is something like reinitiating the mesh machine every 20 milliseconds. So here we have the plankton mesh. I will treat this mesh for now as a simple mesh. So you see that we can also take a mesh component, mesh container, and transfer the plankton mesh to the mesh. Of course, in this case, what we are getting, if I copy paste this panel here, we are getting a standard mesh. Okay, so if we do this, we see the plankton mesh. If we do this, we have just the standard mesh representation. Remember that plankton mesh is a standard mesh, but with a different representation, which is the representation that we were discussing, the half edge representation. So I am going to work with the standard mesh because I want to point out basically the possibilities that we have, and also what are the limits that we have. So what I want to do, I want this mesh to become larger. And if we make this mesh become larger without changing the resolution, we will have the faces becoming larger and larger and larger. So we will have a huge mesh with a very low resolution. So resolution should increase according to the mesh size. What I'm going to do, I'm going to do this. I'm going to increase the mesh resolution as this mesh grows in size. So let's work with the standard mesh representation. I'm going to use the mesh edge component because what I want to do, as I told you, I will not work initially with the mesh itself. I will work with the vertices, so I can convert the vertices into a point cloud and give this point cloud a volumetric representation via the voxel representation. Okay, so this is what I'm going to do first. So we have these mesh edges. I can also take a deconstruct mesh component, so I have access to the vertices. Okay, so these are vertices and edges of the initial mesh, and I will leave this to 10, so very low resolution for our mesh. Okay, so what I'm going to do, I'm going to scale just using a standard scale component, and let me stop the timer so we have a low resolution in a static configuration for now. Yes, we have the scale, and what I'm going to do, I'm going to scale the mesh, and I'm going to extract the vertices and mesh edges of this scaled version of our mesh. And I'm going to use a scale factor between 1.00 and 2. 2 is already a huge scale factor for our purposes. Okay, so by increasing this value, I will have our mesh changing size. So what I want to do, I want to use all these vertices here. You see that if I do this, vertices are separating, of course. And I want to use these vertices, and I want to split each edge in halves as soon as the edge become larger than a given length that I want to consider. Okay, so our edges are all in E2 output because this is a closed mesh, so there are only interior edges, and there are basically there is no problematic edge. Okay, so what I'm going to do, I'm going to measure the length of our edges, and I'm going to say that if this edge becomes larger than a given value, then I want this edge to be split into two halves. Now, we can do this thing in Grasshopper, of course. So let's say that we try to implement this script using visual scripting. So I'm going to decide, okay, so let's see what good value for the B input we can use. So let's double check what's the actual length of these segments here. You see there is 11, 13, 11, 12, 13, 12, 10, 8, 9. Okay, so let's say that as soon as this object starts scaling, what I want to do is I want to have some edges splitting. And I would say that a good value could be, for example, 13. Yeah, the maximum value that we have actually in this edge length. So let's take a slider between 10.00, 13, 15, like this. And what I want to do, I want to split into halves the edges that have a length which is larger than 13. So this is giving us true falses. Okay, so I'm going to dispatch our edges using this dispatch pattern here. So I'm going to take a look at these lines. Let's take a look at these lines and let's see which edge have a length which is larger than 13. These are the edges. There are only 5 lines. I want to split these 5 lines into two halves. So I'm going to shatter these edges, reparameterize these edges, and use a 0.5 parameter. So we have 5 lines here, and now we have 10 lines here by flattening this. Okay, so 10 lines here. And I no longer want the original lines, I want the new lines. So basically what we have here, if we take a line container, we will have the lines that are smaller than 13 plus the 2 lines that basically are the subdivision of the edges with a length larger than 13. Okay, so we have no visual over the shorter segments because they simply are inline, so we don't see any separation between them. But if I take, for example, the endpoints of all these things here, you see that along the lines that we are observing in a few moments ago, we see that the midpoint is being shown. Actually, this is not the midpoint of the original edge. These are the endpoints of the splitted edges. Okay, so what I want to do, I want to use all these points and feed a point cloud. Now, if you have an initial edge like this one, this is the start point, this is the end point. If we split this edge into two halves, this thing here will be the end point for this segment and the start point for this one. So we will have two overlapping points here. And also this is the start point of this edge, but it will also be the start point for another edge, a start point for another edge. So we have overlapping points even in the vertices of our structure. So what I'm going to do, I'm going to use another kangaroo component, which is the remove duplicate points. And I'm going to flatten all of this because this requires a list of points. So you see that here we have 106 vertices or points, and here we have 23. Okay, so these are the 23 points that I want to use in my point cloud, and I do recommend that you install Volvox if you don't, if you didn't do it already. So I'm going to the V here, and I'm going to create a point cloud starting from these points here, and you need these to be a list as well. Okay, so if I turn this off and I turn off also the edges and the deconstruct mesh, you see that now we have these small dots here appearing. This is the graphical representation of a point cloud. And also I want to have an idea of how many how many points we have in this point cloud. So I'm going to plug this and drawing this as draw paths. Let's go away, and I want also a bigger size for this. I want to keep this under control. Okay, so this is the amount of points that are forming my point cloud in this moment. And according to this, if I increase the scale factor, I will have more edges larger than 13, so I should have more points in my point cloud. So let's move this here, and let's see what happens if I try to increase this one. So you see that the amount of points is increasing because we are increasing the edge lengths. Basically, we reach a maximum amount. You see, it's very difficult that things start to increase again, because we are only considering the initial length of the mesh edges. So these mesh edges are just 48. Okay, the maximum result that we can get is to obtain 48 edges, all larger than 13 and all being split into two halves. Okay, so there is no recursive behavior here, so there is no looping. Okay, this is something that we must do later on if we want this to be actually updating automatically. So you see that here we have this in growing point cloud according to the size of our initial object. Okay, and so if we do this, if we have this point cloud available, we can also use Volvox to convert these points into voxels. Okay, like this, and this asks for the point cloud and also for the voxel size, which is the size of the side of one single voxel. So if I say I want voxel between 1 to 10 units per side, you see that we have small cubes here, and if I increase this, you will see that voxels start to blend, and they start to form a single mesh, compact mesh. So basically what we have here is one single mesh that we eventually can give a little smoothness or whatever you might want. So if I decrease these, you see that the voxels are also let's say getting closer and getting less, of course. Or if I increase it, you see that I have more voxels and the shape is getting wider according to our original mesh. So what I'm going to do now, I'm going to loop this behavior. So I'm going to create a loop, start loop, and then just let's repeat the standard procedure. And I'm going to say I want 11 steps, but for now I'm going to use only a few. So what we want to do right now is to take this mesh, the original mesh, and we want to perform all of these operations here inside the loop. So the mesh being scaled is this one. The scale factor is no longer a slider. It will be determined by the loop iterations. So we will take the counter, remap this from its original range to the scale factor actually. And the scale factor actually, I cannot use a single slider as we did before with the angles that we were using for the sine function, because we want the scale factor to range between 1 and 2. Okay, so target domain must be between 1 and 2, not between 0 and 2. So I want to construct a domain and say this will be between 1 and 2. And so this will be the scale factor. So when we release this loop, when we start the loop, we will have the scale factor ranging between 1 and 2. So this thing is going to grow from its original size to double its original size. And this is going to be the mesh. These are the edges. The edges give us the possibility to obtain this point cloud. But in the end, we need to pass to this scale, the new scaled mesh. So I'm going to take the scaled mesh and plug it into this 0. Okay, so when I release this, we will have a growing mesh. And you see that 2, it's quite a lot for our scale factor. So I would recommend that eventually we be a slider, a variable slider between 1 and 2. So we can also change the final size of our object. And also the 13 here is quite a huge amount. So if I do this, I start to have oh, by the way, yeah, the problem is not only that 2 is a huge scale factor. The problem is that if I keep on working with the scaled version of my original mesh, what happens is that if I have a mesh this size, this mesh is going to be scaled the first time just a little. Okay, because we are towards the beginning of the variation of our counter. So this small scale factor should be something like, let's say, 1.1. Okay, but the second iteration starts from this mesh, which is already bigger than the original one. And so if it is bigger, the second iteration produces a scale factor which is higher than the previous one. So it could be 1.2, but not from the original size, from the first scaled version. So this is going to be 1.2 over an already scaled version of our original mesh. Okay, so we cannot do this, because else we have two progressions, one for the mesh and one for the scale factor. That's why the mesh size increases so evidently during the iteration. So what I'm going to do, I'm going to take the original mesh and scale it with a growing scale factor. Okay, and yeah, basically when we do this, as I don't care about the D0, you see that there is no reason for considering the D0. You see that now eventually we have the mesh increasing twice its size, as it should be. And you see that the loop is absolutely irrelevant, because the only thing that we need to consider about this loop is the counter. The counter is the thing that is making our mesh grow in this case. And yes, we have our definition already up and running. Now, this is something that produces this kind of growth, but you can see this. It's somehow useless. Okay, if we consider it like this, we could eventually substitute this new technique that we are using. Can be also a new method for giving thickness to a growth algorithm. So for example, I'm not going to develop this, but you could try to use any of the random growth algorithm that we already created, and instead of using Cocoon, which is quite heavy and cannot work in real time, you could try to use Volvox to create a point cloud and give volume to the pixel, to the point of the point cloud, using voxels. Okay, so this is something that eventually you can try. It's faster than working with Cocoon. Cocoon is a static component, while a point cloud and voxel can be handled almost in real time, especially if a point cloud contains I wouldn't say few points, but not a huge amount of points. Yes. So yeah, this is something that we can absolutely let's say consider, but what we want is not work with a simple scale. Okay, so scaling, yeah, it's interesting because we have a variable resolution for our point cloud, but there is no possibility to control the shape variation of this object. So let's say that I want this object not to scale uniformly like this, but I want this object to interact with something else. Okay, so what I'm going to do as a first step, and we already used some components from these plugins, I'm going to use Kangaroo to rule somehow the growth of this object. Okay, so I'm going to copy paste the initial steps, which are these ones. So I'm going to copy them here, and I'm going to turn this off. Okay. And what I'm going to do, I'm going to take the initial mesh, which is this one, like this, and I'm going to make this thing grow inside a given volume. Okay, so let's start dealing with this kind of problem, because this is probably this is the holy grail of all those who take this kind of course. Okay? So in our mind, differential growth is something that we want to use for, I don't know, filling a given volume with an organic shape. Okay, but we will reach this final step with a progressive complexity path. Okay, so let's do this. We have this mesh here, and what we are going to do, we are going to create a loop, and inside this loop, this time we are going to take into account a more complex behavior. So let's well, even in this case I'm setting this to 11, but in the end I'm just using a few iterations. Okay, so what we are going to do right now is I want to take this original mesh here, and I'm going to pass it. No, I'm not going to pass the mesh in this case. We will get to the mesh behavior later on. I'm going to use the mesh edges component, and I'm going to pass the edges to the loop star. So what I'm going to do right now is I'm going to take these edges, and I'm going to work with this using Kangaroo. Okay, so first of all, let's set up everything with Kangaroo. So I'm going to use a line component just as a dispatcher in this case, and I'm going to use an length line just to give an elastic property to these things. And then I'm going to use also the vertices of this original mesh. Now, as we need to work inside the loop, I'm not going to take vertices from the mesh which lies outside from the loop, because this is a static component with respect to the loop, while our lines will be growing in time according to the loop iterations. So what I'm going to do, I'm going to take the endpoints of all these lines, and as I already told you, there are duplicated points in this set of start and end point. And so what I'm going to do is remove duplicate points once again. So let's go into Kangaroo and remove duplicate points, always flattening this. And I'm going to use these points here because I want these vertices not to get too close to each other. So I'm going to use a sphere collide component with a strength of 1 and a radius of 1. It could also be higher than 1, but for now let's keep it like this, and let's see how this system behaves as soon as we release the simulation. So we have elastic property and sphere collide property. And what we want to do right now is create also a boundary for the growth of this system. So what I'm going to do, I'm going to take a box in Rhino. So I'm going to create a box like here and move it down a little. And I'm going to take this box and move it here and scale it up a little like this. And I'm going to Boolean union these two things here. Just one consideration is that I am trying to avoid trimmed surfaces. Okay, so and I'm going to show you why. So that's why I kept these two boxes with the same width in this direction, because now I can merge all coplanar faces. And you see that here in this moment here we have a trimmed surface. You can recognize it because there are 1, 2, 3, 4, 5, 6, 7, 8 sides for this thing, but this is a standard rectangular surface with a trimmed regions here and here. So we don't want to work with trimmed surfaces. Okay, so what I'm going to do in order to avoid this, I'm going to work with face extrusions. Okay, so I'm going to solids, and then I'm going to use a where is it? Extrude face, yeah. Extrude face, I'm going to extrude this like here, and then I'm going to extrude this like here, and then I'm going to extrude this like here. And this, we must double check. I'm going to use a clipping plane, vertical clipping plane, like from here to here to here. And you see that this is one single volume with no internal partitions. Okay, so this is what we want. One single volume with this kind of strange shape with our object inside. So I'm going to take a B-rep component, set one B-rep. I do recommend that, let's internalize the data so I can get rid of it. I do recommend that you work with this procedure, because what I'm going to do right now is deconstruct this B-rep and use my favorite method for converting a B-rep into a mesh, which is not mesh B-rep, it is mesh surface. So I'm mesh surfacing all the faces of the original object. Okay, this is because it allows a better control over the resolution and the topology of the original, let's say, mesh conversion. Okay. So yep, and we can give a specified resolution to this thing by creating a 11 slider and plug this into U and B. So we get quite a high resolution thing. Yep, here we are. So this is our collision mesh, and I'm going to use Gold's collision solid point collide. So I want all the vertices of our object to collide with our solid mesh, which is this one, and I want them to stay inside our mesh. And now this collision here is a condition that must be very strong, because either I want the point to collide with an object or I don't. Okay, but if I want this collision to be very strong. Okay, so normally I use a strength of 100 when I want very strong forces in Kangaroo. So yeah, basically everything is set with this thing. I'm going to use a solver, a bouncy solver, with a reset button. Eventually we will change this in a second moment, because I want to connect the solver with the loop, but for now I'm going to use a simple standard reset method, and I want this to have a toggle, which by the way also will be changed in order to bind this simulation with our loop. So I'm setting this solver to false, so it won't run when I plug all the goals to the simulation. So yeah, basically this is ready. If I release the simulation, we have this thing is collapsing basically. There is actually the only thing that it's affecting is eventually the spherical light, and yeah, so let's see if everything works just properly. I'm going to use a radius between 1 and 10 for the spherical light. So if I do this, you see that things are moving there. And also I'm going to increase the strength of this. So yeah, you see that now it acts with a little more strength. And also I give more strength to the springs, because if we work with a strength of 100 for the collision, we also must increase the strength for the length line. Now what we want to do is we want this thing to be capable of growing. Okay, so what I'm going to do, I need to take the original length of our edges and multiply this original length by a length factor between 1 and let's say 1.5. and use these as the rest length for our springs. So if I increase this, you see that also this is going to increase our geometry. Okay, and so yeah, basically this is what we get from our simulation. And now the next step, let's say link all this simulation with the loop. The next step is connecting the simulation with the edges manipulation performed by the loop, and see how this object can eventually grow inside our reference or collision geometry. Okay, so if we run the simulation, we see that we have this kind of strange behavior. The fact that the vertices and springs collapse inside the volume is due to this high value for the solid point collide strength, because this is not balanced at the moment by the strength of the sphere collide and the length line. So eventually, for now, I will disconnect this. So you see that now the mesh, or well, basically the point and line structure is maintaining its more or less its original volume. Okay, I'm going to hide also the previous configuration, so we only see the final result of our kangaroo simulation. What we expect to have is this thing growing and adapting to the shape of this volume. Now, let's start analyzing some limitations that we have here. First of all, if I try to increase the edge length, you see that the sphere collide is not enough for maintaining this volume like convex. You see that, for example, there is this concavity here occurring in the lower part, because this condition is absolutely respecting the boundaries set by the sphere collide and solid point collide. We don't want this to happen. We want this thing to basically occupy the volume, which is basically like inflating. Okay. Also, consider that if we decrease the strength of the solid point collide, we might have some points passing through the walls of the solid volume that we are using, as you can see, for example, in this case. But this is not a big problem. We know that we can simply increase the value of the strength and everything will be contained inside the volume. Okay, so this is not good for us. What we want to achieve is that these points well, basically start to expand inside this region. Okay, so what we're going to do now is start to create iterations. So each iteration, each repetition, this thing is going to grow a little more. What's happening now is that each line is being converted into a spring, and this spring has a rest length which is 50% longer than the original length of the lines that are getting in. So eventually, after the simulation, we will have each of these line is 50% longer than the original line. So what happens if we take the lines that come out of kangaroo, like with a line component? Remember that the output normally contains also null items or several types of data. So we don't want this, we just want lines. Okay, so I'm going to clean this tree here. This should be enough for having just a list of the 42 lines that we are using. And I'm going to pass this to the loop end. So basically the loop end is going to send back the lines to the D0 here, and the next 42 line will increase their size by 50%. Okay, so each time we repeat this loop, this thing is going to expand. Now, as you can see in this case, for example, there is no possibility for this object to stay inside the boxes actually, and also you see that 1.5 is quite a lot, so I'm going to keep this very low for the time being, so we will have eventually a more let's say, less drastic effect, as you can see. Of course, each small variation of these is going to produce a huge amplification of the final result. And I want to increase the strength for our solid point collide, so I'm going to try again this with some more strength. So yeah, you see that this is actually taking the lines, endpoints, flattening, and solid point colliding them inside this mesh. So yeah, basically we should have this type of mechanism. Let's see if we, okay, let's first of all, let's try to connect this this trigger here also to the reset and on off status for the bounces over. So when this is set to true, it means that we are exiting the loop. Okay, so the loop is not running. So the loop runs when this is set to false. When this is set to false, this must be true. So I'm going to take a NOT gate and set this to true when we trigger the loop. Okay. And also I want to reset. Now reset, it's true when the Boolean value is true. So when this is true, we exit the loop, and I want also to reset the simulation. And so we start again each time we switch from false to true. Now this thing is evidently is not working. What we need now is to implement, well, what is not working is actually is the collision. Okay, I was expecting this, but I won't take this into account for now, because I want to concentrate in the loop part, and also because this is not the correct way to produce a mesh growth inside a given volume. So let's go for now, let's say from the very basics. So what I'm going to do now, I'm going to implement the subdivision method, and this time I'm going to use a Python script. Okay, and I'm going to use a Python script without, as you can see, we are not dealing for now with the plankton mesh with the alpha edge representation. Okay, so we only need to invoke some methods for the standard RhinoScript libraries. So this is ready to work with a plankton mesh, but we're still not using this this method and this representation. So what I'm going to do, I'm going to take the lines that come out from the D0 loop start output, and I'm going to write a small GH Python script. What I want to do basically with this script is that when the lines that enter this input have a length which is larger than this value here, then I want this line to be split into halves. Okay, so let's call this input here like lines, and the Y is going to be the trigger, so the length that a line must reach in order to be split into halves. So this is going to be the split length. Yeah. And so I'm plugging these lines here. Okay, so let's go into this scripting environment, and you see that it has already an import RhinoScript syntax as RS. So yeah, basically we are ready to go. What I'm going to do, I'm going to create a vector. Well, a vector is a old school name for a list of values, and this vector will be this list will be the output list. So it's going to be A. So I will define A as a list. And what I want to do is that for each item, okay, inside the whole range, which is defined by the length of the lines list. So I mean this is going to loop inside the whole length of the list of lines that we are plugging here. What I want to do, what I want to happen is that let's call L is going to be the I element of the list of lines. Sorry, I element of the list of lines. And what I want to happen is that if, and let's invoke the library rs curve length of the element L is larger than the split length, which is going to be a number connected to split length, then what I want to happen is that add to the A vector, so A, append to this what? Well, let's invoke another method, which is rs add line, and this line is going to start from rs curve start point of the line L that we are considering, and it's going to end in rs curve midpoint of the line L. And let's close all these parentheses. So what's happening here is that if the length of the line that is being taken into account it exceeds the split length measure, then we are going to append, or I mean to insert into the A vector another line that starts from the start point of this line and ends at the midpoint of the same line. And I'm going to A append also an rs add line which starts from rs curve midpoint of element L and ends at rs curve end point of line L, close parenthesis. And if the rs curve length is not larger than split length, then we are going to do A append directly the same element L. Okay, so this is what's going to happen here. If the length of the line is larger than the split length, then the line will be divided into two halves, and if not, the same line will be added to the final list of lines. So let's run a test. Object of type, this is in line 15. I think, oh, okay. This is saying object of type GUI has no length, so it cannot calculate the length of lines. This is saying that basically this input here is not set to calculate the length. Sorry. So I'm going to close this, and this is due to the fact that normally an input is set to item access, but we are providing a list of object. Okay, so that's why if we switch to list, then Python can calculate the length of this vector. And let's test this, and the only thing that we are missing here is the split length. So I'm going to double check what's the length of these lines. Let's see. I'm going to calculate the length, and I'm going to calculate the average. So here we have 22.5. So I'm going to say that split length is going to be something like 20. And if everything's working just fine, we have 42 lines coming in and 84 lines coming out from this GH Python script. So what I'm going to do, I'm going to plug the lines directly from the D0 output. And I'm going to use the A vector for our line creation. Now, as you can see, things are not working correctly here. That's why I told you that this first method is not going to work for differential growth or mesh growth, because what happens here is that initially when the loop performs the first iteration, the edges are basically the edges of the original mesh. Okay, but when we divide these edges into two halves, some of these edges into two halves, we are breaking the original structure of the mesh. That's why you see that the object starts to to break, basically. So if we reset and run this, you see that the object just starts exploding. Okay, so this is not good for creating this containment inside the volume, but I wanted to show you because this is just the first step towards the differential growth using the Python scripting inside Grasshopper. Evidently, in order to obtain the desired result, we need eventually to work with the Plankton library, because if we don't do this, we are basically not taking into account the mesh structure. We are just working with a set of lines. Okay, yeah, basically what we can do with this definition, in case you want to use it for some kind of growth system, we have a set of line here in the zero output of loop end, and basically what we can do is take probably the endpoints of these lines, which is a set of point that grows in time. So if I increase this value, you see that we have this kind of effect on our object. And as you can see, it's like if it was emitting points. The fact that some point just take this grid velocity when they start from this area, probably is because they are inside the radius of a sphere collide. That's why they get shot away from the original position. So yeah, basically that's it. And eventually you could also use these start and end points for some voxeling. Okay, so creating an organic mesh via the voxel behavior. Or if you want another alternative, you might, as we talked about it, you can consider the Heteroptera plugin in terms of networking. So here we have these two set of points, or you can also flatten them into one single point set, like flattening like this, and you can decide whether you want to work with incestuous network or non-incestuous network. So non-incestuous network is if you have two separate sets, you have to create a data tree, or if you want to create incestuous network, you just flatten the two streams into one list of points and then start creating connections between these points. This is just because just for creating some let's say structure which is good for working, for example, with cocoon, as we did before. I'm going to leave this like here, or the alternative, as I told you, is Boltbox with its point cloud. Okay, so these are the main alternatives that we have here. This is going to be one nice point cloud. Okay, so this was just the introduction for starting to use Python to perform this kind of growth things. Now let's jump directly to the last example of our course, and we are going to deal with exactly with differential growth. And what we're going to do now is going to be very interesting. I'm going to also take the same mesh that we were using here, just to create the collision. Okay, so we are going to work with the same object, and I'm going to copy and paste this plankton mesh here, like here. So we are going to start with the same plankton mesh, which is this one, and we are going to perform some divisions, and here it is. So this is our initial object. So what we're going to do now is work directly with this. I don't even need the mesh component right now because I want to work with the plankton mesh. Yeah, let's leave it like this. So remember, the plankton mesh is an half-edge representation of a mesh. Okay, so even if you see triangles here, remember that the main entity of this mesh representation are the lines, are the edges. Okay, so what we're going to do right now is implement a Python script for working with this plankton mesh and performing a division of the alpha edges. Okay. Even in this case, we are going to work with Kangaroo in order to create some growth, okay, inside a loop, but the difference would be the GH Python script. So we are going to take this mesh and put it into a loop, and I'm going to create this toggle, and I'm going to set the number of iteration to let's say very few. Okay, so we want this mesh to go inside the loop. So the moment this mesh enters the loop, what we are going to do is basically implement somehow something very similar to what we implemented here. We need to take the mesh, calculate the length of the edges, and if the length of the edges exceeds a given value, we want that edge to split into halves. Okay, so let's grab a GH Python script and let's start working with it. Okay, so this time what we are going to do is work inside the GH Python script environment directly on the plankton mesh. So the implementation that we are going to do, the script that we are going to do, is basically almost the same as the previous one, just that in this case we are going to work directly with the mesh instead of with lines. So what I'm going to do here, we need, well, Python basically in this moment doesn't know anything about plankton. Even if we have a plugin installed, it's Grasshopper that knows about plankton. So we must make Grasshopper and plankton available inside the scripting environment. And what we are going to pass to this script here are the plankton mesh, let's call it P mesh, and the split length, just like before. Okay, so instead of splitting edges, we are going to split half edges in this case. So basically we are going to work directly on the plankton mesh, and we are going to have here a final mesh result. So what we need to do here is take the plankton mesh and pass it to a P mesh and have a split length. We already know what's the value because it's identical to the previous one, so I'm going to plug here a 20 value. And so let's jump here, and what we need to do in this case, I'm not going to work with random script syntax, so this is totally useless, and we must tell Python to use Grasshopper and plankton libraries in this script here. So we must first of all import CLR in order to be able to read, to import additional libraries in the scripting environment. So first thing, I'm going to add a reference to Grasshopper, and then I'm going to import Grasshopper. That's first thing. And now let's go and add the plankton libraries. So in order to do this, I'm going to CLR add reference to file and path. And this file and path, depending on each user installation, would be Grasshopper folders and default assembly folder plus the name of the library. If you want to know what libraries you must import, first of all, remember to go here on GitHub and install these Plankton libraries, and the Plankton libraries will be available in your special folder, components folder, and they are these three objects here: Plankton DLL, Plankton GHA, and Plankton GH.dll. Okay, so these are the three Plankton libraries that you need to have installed in order to work with this script. Okay, so what we need to do is import, first of all, the plankton.dll. This is the first one. Yeah, and well, I'm going to CLR add reference to file and path, and it is going to be grass with two s's hopper dot folders dot default assembly folder plus the plankton dot gha file. Okay, so now that Python knows where to find this, we are going to import plankton and import plankton gh, and we are going to clr dot import extensions. It's going to be plankton gh dot rhino support. Okay, perfect. So we are ready to go, and what we need to do now is implement the same strategy as we did before with the edges. Now we are going to do it with half edges. So for each item in range, and this range now is going to be p mesh dot half edges. You see that now these things are available in the list of functions, and count. So what Python is going to do is going to take the input pmesh and count all the half edges and cycle between each element of the half edges, column, and evaluate that if the pmesh dot half edges dot get length measure the half edge I and establish if this length is larger than our split length. And if this is true, you take the p mesh dot half edges dot, and what you do on this is triangle split edge I. So this is what the difference with respect to what we did before, because now we are capable of working directly into the onto the half edges, and as you can see, the action that we are performing is triangle split edge, which means that basically we are taking that edge belonging to that triangle and splitting it into two. Remember that one half edge affects two adjacent triangles, so we are basically splitting two triangles with this operation. Okay, and so what we need to do finally is basically send this result to our mesh output, which is this one. So we are going to say that mesh is equal to plankton gh dot rhino support to rhino mesh p mesh, and that's it. If everything is fine. Okay, so what's happening here is that if you take a look at, well, let me hide this thing here so we have a clear understanding of what's happening. You see that this is the original plankton p mesh, and this is the final p mesh, which has 196 faces. Okay, and now if we take a look with a mesh component at what's coming out from this zero output, this has 196, this has 196. If we try to, well, let's work and let's put this into a loop, because this 0 will update, and we are going to see what happens with this. You see that this this has just increased its size. Okay, but anyway, I think I just messed up things a little. Non-type object is not equal to alpha age, probably in line 20. I think, yeah, I think that this is what happened. Okay, so I need to update this, reinitiate the mesh machine, and probably this is not working anymore, because there is another thing calling the method for the plankton mesh. So let's see if somehow we can bypass this. So I'm going to internalize this value here, and I'm going, yeah, you see that now it worked. Now the thing is that once you do this, the mesh is already gone. Okay, so what we are going to do, I'm going to F5, and you see that, yeah, it works. So yeah, basically this is working. Let's bring it back to 20. Now what we want to do with this mesh is use it for a kangaroo series of operations. So what I'm going to do, I'm going to convert this mesh into an elastic mesh. So using the edge lengths. So I'm going to take this mesh and give this mesh a length factor of 1.01. Yeah, well, let's do this. Let's take it from 1 to not to 1.50. Yeah, it's already too much, but anyway. So this is needed in order for us to have this mesh increasing its size each time that we anemone runs one iteration for the loop. And also what we want is to have a spherical light for the mesh. So I'm going to demesh this, and I'm going to add the vertices, and I want them to calculate the collisions between them, and I want to perform a collision with our solid, which is this one. This cube is quite big, by the way, but doesn't matter. Let's see what happens. And the points that I want to maintain inside are the vertices of our cube. And I want them to stay inside, so I need to plug a Boolean toggle with true to the input. That's it. If we see that this is not enough, we are going to switch to pressure instead of a simple elastic and spherical light. So eventually we are going to use this thing here. It's going to make our mesh grow a little faster also. And then we take the bouncy solver, and I want to connect kangaroo simulation to our anemone loop. So when this is true, the loop is inactive basically. So I cannot plug it here. I must take a NOT gate like this. Yep. And the button is basically the same trigger. Okay, and now I'm going to plug the components, not the components here. Yeah, that's pretty it. I think everything is off, like preview. So let's see what happens when we run this. Everything collapses. I'm going to Yeah, that's what I was thinking of. I think we need to work with pressure. Pressure is going to be more effective than this, but we always need elastic force when we work with pressure. So there's nothing wrong with having this method available. So what I'm going to do, I'm going to take the mesh and give pressure a strength between 0 and, or let's say 2 for now. Pressure is a very delicate component. I don't want to exaggerate because things might explode. And so see what happens when we, whoops, yeah, it's already happening. Maybe if we increase the elastic strength, this is not going to happen. So let's take a 10.00 strength for the springs. And so we can increase pressure a little more. Let's see. Yeah, like this. Whoops, once again. Yeah, and also let's increase the strength of our solid point collide, so we will have our solid shape containing this this object. I'm going to set this to 11 and release it. And so let's see what happens here when we start decreasing this a little. We are working just a little bit borderline. Yep, I need pressure because this thing needs to stay unrolled basically, but it's not being contained. Oh, why I have this set of meshes here? So well, maybe this is the problem, because this must be one single mesh. So I'm going to join meshes and weld all of this. So we have just one mesh, and I also want to weld it, even if in this case I think it's not strictly necessary. And now this is not working at all. Let's see. Let's erase pressure contribution. Yeah, here it is. Yeah, maybe in this case also simply working with elastic force it should eventually work. Let's see. We have the object is contained here. Problem is that without pressure this thing is not going to inflate properly. Yeah, here it is. What I want is this object to be contained by this solid, and you see that, yeah, we are actually obtaining this result. You see that what is coming out from the volume here are not the vertices, these are the edges, and unfortunately the solid point collide is only acting on points and not connecting edges. So that's why you always see these edges coming out from the shape, the container. Okay, but this is something that we cannot avoid working with solid point collide. Eventually you must increase the resolution of the initial mesh if you want to have this behaving properly. So let's say that in this case you see that with a little pressure things are working just fine. So what I'm going to do now, I'm going to take the mesh that's entering our bouncy solver. I'm going to have it available after the kangaroo simulation. So I'm going to take a show component, take this mesh and send it to the bouncy solver. So we have the mesh available after the simulation has run. So you see that here we have first output is the mesh. And what I need to do is take a mesh component. This is getting angry because it is receiving also lines and null items. So what I need to do is clean this tree in order to only have the mesh that I need, convert it into a plankton mesh, And so this is the new plankton mesh, and I'm going to send the plankton mesh back to our GH Python script. And so you see that now the loop is closed basically, and this object is growing somehow. Now the fact that you see this messy thing here is because this kangaroo simulation is not actually considering properly the self-intersection for our object. This depends eventually mostly from the sphere collide point. But if you reset this, and I'm not going to consider the mesh aspect. I don't want to see the mesh surface. I want to see the mesh edges, because it is better to see this in transparency, okay, like this. And I'm going to save the file and run the simulation. So you see that eventually you can recognize the shape of this container. Okay, so the problem here is eventually that we are messing things up with this sphere point collide. I'm going to try and change the radius of this. So I'm going to take a 11.00, decrease it to, actually it is 1, so I'm going to decrease it to 1 and start from 1 actually. Also 100 as upper limit is too much. See, each of these dark gray squares are 5 by 5, so I would say that a top maximum value for this should be like 15, 20 top. Okay, so don't exaggerate with this range, and let's see what happens if we start to do this. You see that the mesh is adjusting inside, and this allows a better behavior for our mesh. And also consider that GH Python script is working with a split length of 20, so we need edges with a length of 20 for having a half edge splitting occurring. Okay, so this is quite a huge amount. So let's see what happens if we set this to 15, and let's see what's happening here. Yeah, we have this, and also remember that the strength of the sphere point collide is set to 1, while we have stronger springs and much stronger solid point collide. So I think also that it is a good idea to increase the strength of the sphere collide. Yep, let's see if we go back to 20 and reset everything. I think we are working with a density which is too high for this thing. So what comes to my mind is to start with a low resolution mesh and then have it let's say well adapted to the container that we pretend to use. Or we can also try and use some additional code to maintain this this surface. Let's say flat, but it's not flat. It's like smooth. So I'm going to use exactly a smooth goal. So what I want to do, I want this mesh to stay smooth. Actually, the strength is 1. Let's see if this is enough for affecting our mesh. Well, I think not at all. So I'm going to take another strength slider and see if this helps with our mesh simulation. Well, I think it's too dense. Let me double check what happens with this mesh. Actually, it has 646 faces, and we are starting with 68, so we are getting quite a high density. So let's see if we can Oh yeah, maybe this is the problem. Yeah, okay, so let's see what happens if I decrease this a little. Yes, here we are. Okay, very nice. So yeah, this is it. Basically, we are getting closer. What we need now is to take, for example, let's not consider the mesh edges. Let's double check what happens, for example, if we use a subdivision algorithm like the Catmull-Clark, for example. This is a plankton mesh, of course, so I need to convert it into a mesh object and then pass it to Catmull-Clark. And you see that we are starting to get something that looks exactly like what we expected to get. And yeah, eventually let's see if we can decrease this a little more. Remember that here we have two different actions. We have the GH Python script connected to the anemone loop, which is basically subdividing and subdividing each time that the half edge length reaches this split length value here. And we also have the pressure in Kangaroo that it's increasing the size of this object more and more. This is because pressure acts over mesh polygons. So each time that GH Python script with the half edge method splits a triangle into two, pressure will act on more faces and it will inflate the resulting mesh a little more than the previous iteration. Okay, so we have two contributions to the growth of this system. So let's reset this. And yep, you see that now with just 3 iterations, we are already covering basically the whole volume. Okay, so eventually another thing that we can do in order to try and maintain this thing a little more under control, we could also try and increase the resolution of our container. Just let's see if we have, yeah, we have a valid mesh. Always double check this because as you saw, I forgot to double check what solid I was using, and sometimes, like in my case, I forgot to rejoin all the mesh surfaces that I got here. And sometimes when you do these operations like rejoining meshes or just converting a surface into a mesh or a B-rep into a mesh, you might get an invalid mesh. And if you have an invalid mesh, this thing is not going to work properly. Okay, so always double check this. And what I'm going to do now is, well, let's repeat this. Yep, and also what we can do, we can also increase, let's say, a couple more steps. Let's see what happens. Yeah, here it is. And we have this characteristic curly aspect for the resulting mesh, that it's filling up this space here. What I'm going to do now is take, for example, a mesh sphere EX, like this one. Let's reset everything. The mesh sphere EX is basically just like an inflated cube. Okay, so here you decide how many polygons you have for this object. I'm going to exaggerate. I'm going to take like a slider 20, and I'm going to take a radius of well, originally this should have a radius of 10. Yeah, so I'm going to take a slider 11. So you will have this nice mesh here. And we are going to use this mesh, which is a closed solid mesh, as the container. And so let's see what happens when we do this. And I'm going to hide the container. So you see that you have this characteristic curly aspect, typical of differential growth for mesh, three-dimensional growth. And so with this, you can obtain very nice results in terms of mesh growth. So as you can see, this object here, if we take a look at it with the Arctic rendering, you see that it presents this kind of concavities depending on the growth portion. You can also take a look at it like this. It should be, let's say, more interesting if things become more interesting, for example, if you set a different elastic behavior for this original mesh. So I'm working with the edge lengths here, which gives the whole mesh, the whole edges, the same elastic property. Okay, but I could eventually assign a different elastic property to different areas of the mesh itself. And so basically, what would happen is that pressure would affect some areas more than others, and then you will have a let's say more variable growth for your system. So basically, this is like creating elastic weakness in specific areas or in random areas as you please. Okay, and the other thing, the last thing that I wanted to see here is that we have this sphere point collide that affects how the mesh, let's say, can relax, or it's forced to create this kind of protrusions here. Okay, so much depends on the self-collision of the points. And don't exaggerate with this, because else the action of this sphere collide becomes too strong and eventually globally stronger than the container itself. Okay, but if we consider, for example, let's consider a more complex shape. So what I'm going to do now, I'm going to stop this simulation and just double check that everything is working fine. Instead of using this thing, which is pretty simple, what I'm going to do, I'm going to take front view. I'm going to take something like this. Something like, yeah, this. And I'm going to take this curve and extrude it solid both sides like this. Yeah, here we are. And I'm going to take this B-rep, set it here and internalize it here, so we don't have the solid object in Rhino. And I'm going to mesh B-rep this. Now I don't like to work with mesh B-rep because you have this kind of let's say lack of control over the topology of the mesh. You will have eventually vertices along the edges, but no vertex on the surfaces of this object. So you should work with these with the settings if you want. I'm not going to go into these details, but basically the settings that you have here are the same settings that you can find in the mesh details when you select the mesh objects here in when you select an object here in Rhino, you can select the mesh properties here in the object property panel. Okay, so these are exactly the same things that you can set here in this area. So aspect ratio, maximum grid size, minimum grid size, simple planes, and so on. So this is the mesh that we are going to use as the collider. Let's reset everything, and you see that the object expands exactly inside this this shape. Eventually 5 iteration is not enough to fill the whole space, but if we increase this, you see that, oops, with 7 we are already done. Of course, the more you let this thing go, the more this mesh will tend to expand, and so it will tend to form concavities and curls and so on. So you can see that this thing is already expanding throughout the volumes, and it's creating this kind of nice concavity in this area. But if you increase this too much, then you will have some undesired effects eventually, sooner or later, because soon the topology of the mesh becomes too dense, and so the mesh becomes too strong, and it alters the balance between the forces in the kangaroo simulation. Okay, but you can see that in this case, for example, we are still working inside the limits, so you have this kind of a nice filling for our region. Let's double check with an Arctic render once again. So I'm going to bake this, and here it is. We have this mesh. You see that it is already borderline. You might notice that there are some, let's say, artifacts here in the mesh. This means that the mesh is already behaving in a weird way. Okay. Also, in this kind of simulation, one thing that is quite important is you should start your simulation always with triangular polygons. Okay, so for example, you see that plankton meshes. Well, let's exit the simulation. Plankton meshes. If you take a look at, let's deconstruct mesh this, and faces, you see that here we have T. Okay, so always double check that you are working with triangular faces, because these methods work with triangular polygons, and this is very, very important. So always double check that you have the right type of mesh. And oh yeah, of course I came back and started to work with this one, so I'm going to undo. Yeah, okay, so here we are. So always remember, don't exaggerate with the amount of steps. Of course, the amount of steps depend on how far you need this growth to reach, for example, for the extreme part of the container. Okay, but in this case, for example, you see that this is actually working perfectly with a smaller amount of iteration. It's already reaching filling the whole volume, so there is no need to create more and more repetitions. What you might do if you want to use more repetition, you should allow the plankton mesh to have shorter edges, so that it becomes more and more detailed. Just remember that this kind of simulation can become very, very heavy when it's being calculated. Okay, so for example, if I set this to 10 and I toggle this, you will notice that the mesh is capable of having more and more and more curly areas in its inside, and you see that the simulation starts to run quite slow. Okay? But this is pretty normal, so you just wait for it to end, and you're done. That's why I was setting the number of iterations to a very small value. Okay, so now we wait for the 8 repetition. Let's see at how much we are now with the counter, but I think we're pretty done. Yeah, that's the 8. And remember that when this reaches the 8 value, kangaroo is still calculating. Okay, so remember that the loop is affecting the GH Python script, but once the mesh comes out from the GH Python script, it's going to be used by Kangaroo. And the fact that we are using a 10 split length produces a mesh with a higher resolution, so Kangaroo is actually performing quite a complex simulation. Okay, and also we are getting a denser mesh with many edges, many vertices, so we have to establish a different balance between the strength of these goals and the solid point collide, because it's pretty evident that the final mesh is basically passing through the walls of the container. Let's wait for this to show me the Kangaroo, which is still calculating. Yeah, here it is. It says running, and this is going to calculate quite a lot. Okay, so let's switch to wireframe the moment that Kangaroo allows to do it. Yeah, here it is. So you will see that this mesh is quite dense as soon as we, yeah, here it is. You have it. Yeah, what I'm going to do, I'm going to take this mesh container and I'm going to internalize the mesh, because actually the loop has finished this its iteration, and I'm going to take the bounces over as soon as it gets selected, and I'm going to disable it so it won't be calculating anymore. And here we are, we have our final mesh. I'm going to also exaggerate a little with subdivision, so to get a very complex result. Of course, I am using a Catmull-Clark, which is basically creating squares from our triangular mesh, but you can also use any other subdivision algorithm like loop, for example, that maintains the triangular aspect for your mesh. So I'm going to bake this. Well, there is no need to bake because this is to group, because this is just one single mesh. By the way, it has let me double check, 392,000 polygons. Okay, so 400 polygons, quite a high resolution mesh. So here it is, we have our fantastic curly organic mesh with no self-intersection, I suppose. I see some weird areas, but I see no self-intersection, which is very good. This is actually a closed mesh. It can be sent to production. Let's double check, for example, with a clipping plane, vertical clipping plane, or, well, yeah, clipping plane, whatever, horizontal, it's good enough. Yeah, you see, for example, like this is a very common test that it's performed to double check that everything is working properly. Oh, you see we have a self-intersection here. Here it is, and also here. So this is something that you might want to adjust by tweaking the for the strength of Kangaroo goals. Also, maybe here, yeah, that's the little. But remember that these things are the things that that mess up the work when you want to send these objects to production. Ooh, look at this. Okay, so this thing is something that you want to avoid, definitely. But anyway, it's just tweaking the strengths of Kangaroo goals. Yeah, here it is. Nice result. And you can also take a look at this in a rendered viewport like this one. Okay, so this was the last step. We have examined a whole range of growth algorithm, and oh, let me before. I want to share this file with you, of course, so I'm going to exit this loop, and I'm going to go back to a more let's say light version of this thing. So I'm going to increase the split length, and here you will have some options. All these things are internalized, so you can decide which mesh you might want to use. This is somehow more chair style. This is a freeform. This is a sphere, and this is a let's say solid, linear solid, very basic. Okay, so I'm going to take a mesh object here and pass through this. So I'm going to create a switch in this area like this. But this is something that I normally do when I have variable selections that I can make in a particular area of my definitions. So I create this kind of structure here and group it and give a yellow color. So I visually know that here I can decide between three different inputs what's the object that I want to use as the container. And you see here, for example, how far we went out from the container, the wannabe container. This is because of the forces that we have been using, especially the spherical light that is acting with a huge power in this case. Yep, that's pretty it. So we went through a whole range of growth algorithms, from the very basics and random or pseudo-random algorithms to some more complex script driven growth algorithm for a plankton mesh or half-edge mesh representation. I strongly recommend that you get deeper into half-edge theory, and also keep in mind that in this final script that I have created, that I'm going to reconnect here, in this final script that I have implemented here, there is the only problem, which is, by the way, it's quite a huge problem, is that we are mixing scripting with plugin, like Python scripting with Kangaroo. So Kangaroo is actually generating the size variation, okay, while Python is adapting the half-edge structure to the new size by subdividing the edges that are too long, okay. If you go into Python a little more, you will find libraries that allow to calculate collisions inside Python, and therefore you can program all this behavior inside Python, which makes the simulation way faster. The reason why I am not doing this in this video course is because it requires the installation of a whole let's say virtual machine, let's call it so, environment, where you must install all the Python language and all the modules that you want to have available inside Grasshopper, and then connect this virtual environment in your computer to Grasshopper via a plugin. So it's quite difficult, it's quite complex, and it's quite long as a process. While in this case, you get the idea of what you need, and you can create a complex set of scripting and plugin in order to have this behavior up and running. Okay, so finally I'm going to take all this definition here, and I'm going to share it with you on my web server. So I will share with you the link to download this file that comes with all the indications for having it up and running. Just remember to install all the plugins that I have mentioned here in this list, and to download the Plankton library from the GitHub page that I have placed here in this area. And I'm going to turn everything off in this definition, so disable everything. So I'm going to save it for good, and here it is. So thank you very much for taking this course with me. I hope you enjoyed it, and I hope you will find it useful in your professional practice. Bye.